Hello physics students. So today we're going to be talking about another kind of wave, the electromagnetic wave. So if I take this plastic object and this fur and rub them together, this plastic rod will acquire a negative charge as we learned in the electrostatics unit. So this negative charge makes an electric field all around it pointing toward the rod. But if I take this rod and I start wiggling it or moving it in simple harmonic motion, what will happen is the electric fields will also wiggle or vibrate. And then that electric field and also, it turns out, a magnetic field caused by the moving charge, something we didn't really talk too much in the magnetism unit about because the topic was so short. The magnetic field will also wiggle, and I'll have a wave of electric and magnetic fields. We call those waves electromagnetic waves. So that's the topic for today, electromagnetic waves. So the first thing, what is the source? You have to vibrate a charge, put it in simple harmonic motion or any kind of acceleration, and that'll produce, but mostly, you want it to oscillate. You'll get this wave that has both electric and magnetic fields. Now this is a little tricky to draw because it's in 3 dimensions. The wave is moving this way. The electric field is vibrating this way. As you could see, I got like a sine graph here going. And then the magnetic field oscillates perpendicular to that. So I'm trying to draw a field that's like 90 degrees to these, so you kind of see oscillating horizontally like this. And then those waves have crests and troughs of electric and magnetic field. So electromagnetic wave is a transverse wave of electric and magnetic fields that can travel through a vacuum. That's the important difference between this wave and sound. Sound was a longitudinal wave. This is a transverse wave. Sound could not travel through a vacuum because sound was vibrating atoms. Here, electromagnetic waves can go through a vacuum because electric and magnetic fields can exist in a vacuum. And they can also go through matter, not always, but a good deal of time. They can go right through matter, solid objects even at times. So let me create a pause, let you copy this down. All right, so very interesting though, because if I oscillate this rod at a certain particular frequency, then the wave will have that same frequency. In other words, if I oscillate this 10 times per second at 10 hertz then the wave of the electric and magnetic field as it's passing past objects will also have a frequency of 10 hertz. But if I shake this faster and faster, suppose I could shake this 10 times 10 to the 5th power. In other words, I could shake this up and down 10,000 times in 1 second. I can't, but let's just suppose I could. I would be creating a radio wave. In fact, if I shake this faster and faster, and let's take a radio wave of 1,010,000 hertz. So if I could shake this up and down 1,010,000 times per second, I would be creating an AM radio wave. That's all that an AM radio wave is. In fact, what I just named is the frequency of 1010 on the radio. When you hear the news, the AM wave, AM radio dial 1010 wins, we give you the news. So if I could shake this that fast 1 million times per second, then what would happen is if I were near a radio that were playing 1010 winds, it would get some static. I'd start interfering with the radio waves that are coming from the antenna of the radio station because I'd be making my own waves and the radio would be picking that up on top of the radio waves of the radio station. So that's all that's happening when they're making AM waves. They've got an antenna where they're oscillating electrons up and down on that antenna, and that produces an electromagnetic wave of that particular frequency. But if I shake faster still, I can get into the FM radio wave range. So we'll take a radio station like Z100, 100.3. If you look at your radio closely, it will say 100.3 megahertz. 1010 on AM says 1010 kilohertz. So I added 1,000, that's how I got 1,000,000 hertz for the oscillation of 1010 radio station. But Z100 was 100.3 megahertz. That's the actual unit of the radio station. That means in the antenna of Z100, the electrons are oscillating up and down 100,300,000 times per second. So if I could do this 100,300,000 times in 1 second, I can't. But if I could, I would be interfering with Z100, and then people trying to listen to music, all of a sudden there's static of me doing this, interfering with their radio waves. So where am I getting these numbers? Well, off the radio dial, but how did I know that was AM and FM besides, just what the radio says? Well, there's something in our reference table, the electromagnetic spectrum, a big thing on page 2 of the reference table. And so, I'll just show you this briefly. So as what I was talking about are the AM and FM waves. This is the electromagnetic spectrum of all the different particular waves that can be created from vibrating electromagnetic fields. So I'll talk more about this spectrum in a minute because I just want to go through. I go faster and faster. I could start creating microwaves. So if I have a glass of water here and I'm shaking, in the billions of times per second, I could maybe heat up some water. Also, your cell phones work in the microwave range. That's how they're communicating. So yes, your cell phone is sending out, there's a little antenna in there and it vibrates the electric and magnetic fields very rapidly. And the electrons very rapidly. It sends out these electromagnetic waves and those get to the tower. And so, just from your cell phone, these waves are largely, most of them are invisible. They can go large distances of miles and be used for communication. If I start shaking this even faster, let's suppose I get to like 4 times 10 to the 14th. There's not even a word for that. It's beyond billion, beyond trillion. So I guess, let's see, a billion is 9th, trillion is 12th. So I guess I would say 400 trillion times per second. If I could shake this, something even more interesting happens. I'd be creating an electromagnetic wave, but you wouldn't see this because it's oscillating so fast. And right in this vicinity, what you would be seeing is a red glow. And you would see instead of this a red light coming toward your eyes. Why is that the case? Well, because it turns out that light is within the electromagnetic spectrum. In other words, light is nothing more than vibrating electric and magnetic fields. And if they vibrate, those fields, down here, in this range, at 10 to the 14, 10 to the 13, 10 to the 12, those are invisible to the human eye. They cannot see these waves, infrared, microwaves, your cell phone signals you can't see. But in this narrow range over here, right here, suddenly your eye can respond to any frequency in here and it sees the different frequencies, it perceives them as color. So if I shake between 4.82 and 5.03 times 10 to the 14th hertz, that creates orange light. Shake faster, yellow, green, blue, violet. Between these two frequencies, the region where I was shaking that rod, if I could shake it that fast, would be glowing violet, like a purplish color. And then if I continue shaking faster, beyond this frequency, my eye cannot detect those waves anymore, and I start creating ultraviolet rays. So this could cause sunburns, things like that. Shake even faster between these frequencies, 10 to the 16th, 10 to the 20th. You get X-rays. Shake even faster, you get gamma rays. These things all cause cancer up here because of the high energies, which we'll talk about later in the year. So that's all that all these waves are. They're all the same in the sense that they're vibrating in electric and magnetic fields. It's just when they vibrate at different frequencies, we call the waves different names. Notice also there's overlap. If some wave has a frequency of 10 to the 17th hertz, you could either call it an ultraviolet ray or an X-ray, and it's perfectly fine. Either way, you get the question correct. Same overlap over here. It could be infrared or microwave. So you could call either one. The reason why, that's a historic reason, people were studying different things. They called them different names, and at the time, they didn't realize they were studying the same waves. So there's a little bit of overlap there. So that's the electromagnetic spectrum. You need to be able to use that spectrum to answer questions about, identifying waves. All right, so electromagnetic spectrum, page 2 of the reference table. Obviously, we're not going to copy it because you have the reference table for your quizzes, tests, and the Regents. So I just put that in your notes that you know that that's in the reference table. Now, just like sound traveled at a certain speed. These electromagnetic waves also travel at a certain speed. But it turns out that we don't call that speed the speed of electromagnetic waves, like we say speed of sound or speed of electromagnetic. We don't say that. We call all of these speeds the speed of light. So even though light is just one of the many, you find the speed of all these waves on the reference table, front cover. We already saw this in the gravity unit, but near the top, speed of light in a vacuum, it has its own symbol C, and it's approximately 3 times 10 to the 8th. It's a little bit less than that, but this is close enough for our significant figures in our usage. So the speed of light gets its own symbol because it's such an important concept in physics. It shows up in a lot of theories in very fundamental, powerful ways that physicists decided it needs its own symbol. So when you see C, it means the speed of light, 3.0 times 10 to the 8th in the reference table. Also, for calculations, you have to remember that like all waves, you might be using this formula to relate the distance and time that the wave travels, and also this for the relationship between frequency and wavelength. So let me create a pause to give you a chance to copy these notes down. All right, let's move on. I'm going to do a couple examples. Okay, example 1. How long does it take light to reach us from the sun? So this is a question where we're looking to relate find the time from how far away the sun is. And so what we do is we start with D equals VIT. Of course, that's right off the reference table, page 1. There's also a 1/2 AT squared here. The light's not accelerating, so we leave that part of the formula off. Now, we need a distance. That is actually on the reference table. So right here, front cover, right here, mean distance Earth to sun, and you see if you look across, it's 1.5 times 10 to the 11th on this side over here, right there, 1.5 times 10 to the 11th. So that's what we substitute in for distance. The speed we get from the front cover, as I mentioned, speed of light, 3 times 10 to the 8th. Time is unknown. Divide by 3 times 10 to the 8th, and you get about 500 seconds. And that turns out to be about 8.3 minutes, I believe. You know, just for reference. So, let me just give you a chance to copy this down before I comment. All right, so that's quite a bit of time, but the sun and the earth are very, very far apart. That's why it takes so long for the light to get to us from the sun. So, like, let's suppose something strange happened and the sun shut off and, went out for some reason. And we would be looking at the sky and say, whoa, what a sunny day for 8 more minutes. We wouldn't even know because the light's still traveling to us for 8 minutes. And then finally, when it shuts off, then we would finally detect that the sun went out. So anything that happens on the sun, we're going to see it 8 minutes later. But just to give you an idea of how fast light is, some distance is a little bit more tangible. We know about how far it would take to walk around the Earth, maybe around the equator, if you could walk around the equator. So light it could wrap around the Earth. If it could go around in a circle, it would go around the Earth 8 times in just 1 second. So that's how light is extremely fast, that 3 times 10 to the 8th velocity. All right, let's do another example. Okay, this is kind of a classic question, light type question on the Regents. So you got an electromagnetic wave, they give you the wavelength, and they want you to determine the frequency. That's part 1. So what you should realize to find frequency is you're going to use the relationship between wavelength and frequency. V equals wavelength times frequency. Again, I mentioned that's in the reference table on the wave section, so you don't have to memorize that. The speed of light we get, or speed of any electromagnetic wave we get from the front cover, 3 times 10 to the 8th. Of course, we need the units. The wavelength, frequency unknown. We divide by that 5.25 times 10 to the minus 7th, and we get a frequency of 5.71. Okay, there's the frequency. The next part, identify the type of wave. We use the electromagnetic spectrum, and we go and we look up what that would be based on that frequency. So we see here again, the spectrum. We see 10 to the 14th is somewhere between 10 to the 15th, 10 to the 14th. Maybe it's visible light then. So we look down here. Again, it's 5.7 times 10 to the 14th, and we see that that falls between 5.2 and 6.1 times 10 to the 14th. So it's right in between here, these two numbers. What is that kind of wave? That is green light. Right there you can see. So that's the answer to what type of wave it is, green light. Okay, let me create a pause to give you a chance to copy this down. All right, moving on. You may have heard that of sunglasses that are polarized. Polarized sunglasses. What does that mean? Well, what I have are 2 sheets of plastic that are polarized. And so if I hold this in front of my face, you see that it kind of makes it a little more dull, like a grayish color. But that's not really the feature of a polarizer. To see what a polarizer does and why it's very useful, I'm going to put 2 polarizers in a row, and you see that it doesn't really look like much has changed. But what I'm going to do is turn this polarizer 90 degrees. And you see, you can no longer see me anymore. If I continue and turn another 90 degrees, you can see me again. So this illustrates nicely the effects of a polarizer, but it'll help us understand. Now, if I show you a model of a polarizer, what a polarizer is it's a series of microscopic, very small grooves on a piece of plastic or a piece of glass. And what that does is it only allows certain direction of vibration to pass through the polarized sheet. So if I take a spring here and I shake it, you could see I could make this shake up and down, or I could make it shake side to side. But if I pass the wave through a polarizer, these grooves will now only allow up and down vibrations. If I try and send a side-to-side vibration, it will not pass through the polarizer because of the grooves. So side-to-side doesn't pass through, right? But up and down does. But if I turn this polarizer, now up and down no longer passes, but side-to-side does. So that is, it makes only certain direction of vibration pass through. So what I'm going to do is try and diagram that so that you can understand that pattern. Let's say we've got random light. It's vibrating every which way in this room because there's no polarizer. And then I have polarizer 1. What that does is when the light emerges here, it's now polarized. It can only the parts that are vibrating up and down out of all these random can pass through. So this is polarized light. And then if I put a second polarizer as this light's traveling, and I put this now horizontally, what happens now, because only now side-to-side light can get through, this up and down light cannot go through, so we get no light here. So let me create a pause to give you a chance to copy this diagram down. All right, so polarized light, as I said, is used in sunglasses. Very useful because when light reflects off of surfaces and gives you glare when you're, say, driving, you don't want the glare because it makes you blinded and you can't see. You put the polarizer, and the glared light, which is polarized by the reflection partially polarizes it. If you put the glasses and have them designed in the right way, it'll block the polarized light that's reflecting, so the glare gets blocked, and then you could see everything else around you. So it blocks glare. That's one way it's useful. Another way that you use polarized light is if you went to a 3D movie. What would happen is, in order for them to get you to see 3D, they need you to see one image, one movie with your right eye and another image or movie with your left eye. And then when you see two, that's how you can detect depth, is that you can see differences in what one eye sees versus another, and then you could tell how far away something is. So to allow you to see two different movies on the same screen, they polarize one movie this way, one this way. It's the same scene, but it's just from two different angles. So they have two cameras recording the scene to make a 3D movie. And then they project those two images right on the same screen. And then they put one polarizer in front of one eye, one in front of the other. And this one blocks the images that are intended for this eye. And this one blocks the images that are intended for this eye. And so you can see the two separate movies and see the 3D. Very interesting, fascinating application of polarized light 3D movies. If you're at a 3D movie, borrow your friend's glasses and take them and go like this, and you'll see that you can create this effect of sometimes the light passes, turn the glasses a little bit more, and sometimes it blocks the light. You'll verify that the 3D glasses are polarized. That's the way they achieve that magic. So that's electromagnetic radiation. So just to recap, it's vibrating electric and magnetic fields. They're transverse waves, meaning the vibrations are like this when the motion's like this, perpendicular vibrations to the wave motion. They can travel through the vacuum because electric and magnetic fields can exist in a vacuum. That's why we can see the sun, but we can't hear it. The sound of the sun can't get through space, but the light can, and other kinds of radiation, electromagnetic radiation. And then be familiar with the electromagnetic spectrum in the reference table, be able to identify waves and understand how to use this to identify waves. And then the basic calculations, D equals VIT and V equals lambda times frequency that we've been using with all waves. They work with these electromagnetic waves, provided that you look up the speed of light. So again, speed of light works for gamma rays, it works for infrared, it works for X-rays, radio waves, all of it is 3 times 10 to the 8th, and then you might solve for frequency or wavelength, and then a little bit about polarizers. So I hope you enjoyed the physics, I hope you enjoyed the video. I'll see you in the next physics video.